right, everyone, in this video we will discuss, again, Markovnikov versus anti-Markovnikov determination and do more practice with that. If we react this alkene with a proton electrophile, we can imagine forming the positive charge either here or here. We have primary alkyl versus tertiary alkyl. The more stable carbocation would be the tertiary alkyl carbocation, which I'll draw over here. Then, in the next step, Br- would attack and bond to the tertiary carbocation, forming this product here, which we would describe as the major regioisomer, which is the Markovnikov regioisomer. If the carbocation were to have instead formed at the less stable site, the primary alkyl, and the bromine attacks there, that would then give rise to the minor regioisomer that would be formed in a lower yield. That is the anti-Markovnikov outcome. But the carbocation is going to form preferentially at the site where it's more stable to be formed, which is this tertiary alkyl, and therefore the higher yield of our product obtained has the bromine bonding to that Markovnikov position. So we'll annotate over here, Markovnikov, anti-Markovnikov. All right, looking at this next example, alkene reacts with HI. Let's form a positive here versus here. Visualize that together. The top position is tertiary dibenzylic, resonance stabilized by both benzene rings, versus secondary alkyl. The more stable carbocation would be here at the tertiary dibenzylic position. I- would then attack and bond, producing the major regioisomer, or Markovnikov outcome. If the positive charge instead formed at the less stable site, the anti-Markovnikov carbon, iodine attacking and bonding there would give rise to the anti-Markovnikov outcome, or minor regioisomer. So we have our Markovnikov and our anti-Markovnikov positioning. Now, when you combine water and acid, an acid catalyst with water, water is going to pick up a proton from sulfuric acid forming hydronium, essentially the protonated form of water. When the alkene pi bond reacts, it would grab a proton from hydronium, and we'll imagine the carbocation stability here versus here, tertiary benzylic versus tertiary alkyl. We'd much rather form the positive charge at the tertiary benzylic position. The carbocation would form there, then water would attack and bond. As water bonds to that position, tracking with you, the oxygen would take on a positive formal charge. And then we would have other water molecules in solution come over and deprotonate that oxygen atom. And that would then leave behind a neutral OH group identity. In other words, when we have a water nucleophile, when it adds, the net result is we form an OH group. That's our major regioisomer or Markovnikov outcome if the positive charge instead formed there and water attacks and bonds and then is deprotonated. We get our anti-Markovnikov alcohol product. But the major product formed is the Markovnikov outcome at the tertiary benzylic position. Now, similar to water reacting with acid picking up a proton, an alcohol can react with acid to pick up a proton, forming the protonated version of that alcohol. With this alkene pi bond, we react with that proton from the protonated alcohol. We'll imagine a positive here versus here. We have tertiary alkyl, but that would be then destabilized by the oxygen atom because it's not directly bonded to the oxygen. The positive charge forming here is technically only primary, but I'm noticing that if the positive charge were to form there, we could have a full octet resonance structure generated. So that would be hugely stabilizing. Therefore, the positive charge would form preferentially at this position bonded to the oxygen such that we could achieve resonance stabilization. Let's imagine methanol then attacking and bonding. The oxygen from methanol would share its lone pair with the carbocation, forming a bond. More methanol in solution would then deprotonate, removing that hydrogen to leave behind a neutral OCH3 group. The minor regioisomer would form through that anti-Markovnikov carbocation. Alcohol would have attacked and bonded. We then remove the hydrogen from the oxygen, and that forms our minor regioisomer. So here the Markovnikov carbon is the less substituted position, but nevertheless it's the more stable site for the carbocation to form at. And you'll notice that whenever we react with an alcohol, the net result in terms of the group that we generate is the OR group, oxygen bonded to its carbon chain. In this next example, we electrophilically add our proton from HBr. We'll imagine a positive here versus here. This would be tertiary alkyl because it's not directly bonded to the bromine. The bromine would withdraw, inductively destabilizing that. and if the positive charge forms at the carbon directly bonded to the bromine, that would actually be more stable, because when the positive is directly bonded to that bromine, we could then have resonance stabilization of the carbocation through a full octet contributor. Therefore, the positive charge would form here preferentially, and then Br minus would attack and bond to that position to generate the major regioisomer, our Markovnikov outcome. If the positive charge formed at the anti-Markovnikov and bromine bonded, we would get our minor regioisomer. All right. So notice we didn't focus on the stereochemistry aspect of the addition. Here, this exercise was purely looking at the regiochem, identifying Markovnikov and anti-Markovnikov, and practicing visualizing major versus minor outcomes.